So welcome to today's INQA seminar. Very pleased to have Vrinda Mehta from the Forschungszentrum Jülich in Germany, who's giving today's seminar. And Vrinda is going to be talking about quantum annealing and its variants, application to quadratic unconstrained binary optimization. Over to you, Vrinda.
Thanks a lot for the introduction, and thank you everyone for joining. I will start right away. Okay, so the outline for today's talk. So I'll start with a brief introduction for quantum annealing and some of the related concepts. And then I'll dive into the results for the performance of what we call the standard quantum annealing, which is done using both numerical simulations as well as the D-wave quantum annealers. And this performance would be gauged using what we call the scaling efficiency or the sampling efficiency, terms that I will describe in a short while. And then I will talk about the effects of introducing certain modifications to this standard quantum annealing algorithm. So this is done via simulations, and these additions, these modifications include the addition of an additional Hamiltonian to the standard quantum annealing Hamiltonian, which we call the trigger Hamiltonian, or modifying the initial Hamiltonian for quantum annealing. I will then summarize with the main findings of my work. Okay, so let us start with the optimization problems. So let us consider that at hand, we have an optimization problem, which involves some cost function that has n variables. And we need to find an assignment to these n variables that would make the optimization function optimized. There are many physically inspired techniques for solving such problems, which require to map these problems onto some Hamiltonian. And one such technique is that of simulated annealing. So here we explore the energy configuration, energy landscape of the problem using thermal fluctuations to find the energy, the configuration that corresponds to the smallest energy. However, if the potential barrier becomes high in some case, the state of the system can get stuck in a local minima, thereby restricting our search for the global minimum. Then the idea of quantum annealing is to replace these thermal fluctuations by quantum fluctuations in the hope that doing so will still facilitate the search for the configuration with the lowest energy using quantum tunneling. So how is this done? For this, we have what we call the standard quantum annealing Hamiltonian, which is given by this equation here. Here we have these annealing functions, A of S and B of S. So they control the schedule of our annealing. And S is just the annealing parameter, which is defined as the ratio of T, the instantaneous time, to the total annealing time. So the problem Hamiltonian is basically the Hamiltonian encoding our optimization problem that we are interested in solving. And the initial Hamiltonian is typically chosen to be this transverse Hamiltonian. So in our simulations, okay, so for the method to work, we require that the annealing functions, so A of S and B of S, are in a certain way so that we can do the annealing. So we require that at S, small s, that means in the beginning of the Hamiltonian annealing process, we require that A of S is much larger than B of S, so that we start mainly with the initial Hamiltonian. And at the end, we require that B of S should be much larger than A of S, so that we end in the problem Hamiltonian. So in my simulations, I used linear schedules for A of S and B of S. And all the involved quantities in my simulations were unitless. However, if we do the experiments on the D-wave quantum annealers, then the schedules A of S and B of S are given in the units of gigahertz. And therefore, if we want to find a correspondence between the annealing times, for example, using simulations and the D-wave, then we need to use the annealing schedule from the D wave to convert our units to physical units. Okay, so the success of quantum annealing is based on what is known as the adiabatic theorem, which basically states that if your system starts in the ground state of the initial Hamiltonian, so at s equal to 0, and if the sweep from the initial to the problem Hamiltonian is slow enough, then the system always stays in the ground state during the evolution. So slow enough here is characterized by this quantity delta min, which represents the minimum energy gap that occurs between the ground state and the first excited state of the annealing Hamiltonian. So in this figure, it is this point of anti-crossings between these two levels. So put mathematically, the adiabatic theorem says that the annealing time that is required to ensure an adiabatic evolution should be much larger than this quantity on the right-hand side. So from here, we see that this quantity delta min is crucial for the performance of quantum annealing. And more specifically, if we find for a certain set of problems that this minimum energy gap closes polynomially as the size of the problem increases, then these set of problems should be easy for quantum annealing to solve. On the other hand, if we find that the minimum energy gap closes exponentially as the size of the problem increases, then the problem should be relatively hard for quantum annealing to solve. So how do we then gauge the performance of a certain method to solve an optimization problem? For this, in our work, we use 3 performance metrics. The first is what is known as the success probability, which is basically the probability to find the solution to the optimization problem that we are interested in. So in case that the solution is already known, this is a straightforward quantity to compute. In other cases, near to optimal solutions or solutions that satisfy all the constraints can be used to compute, get an estimate of the success probability. Another metric for gauging the performance is the scaling. So for example, in this case, the scaling of the minimum energy gap or the time to solution as the system size grows. Then for problems which have more than one possible solutions, another quantity of interest could be to see the efficiency of a method to yield the different solutions of the problem. And this is what we call the sampling efficiency. Okay, so with this, I come to the set of problems that were used mainly for this work. And these are the 2 satisfiability or the SAT problems. So in these problems, we have the cost function, which is a function of n Boolean variables, which we denote as xi. And the cost function is then a conjunction, which is an AND operator between m clauses. And each clause is a disjunction between 2 literals, which means an OR operator between 2 literals, where a literal can be the binary variable xi or its negation xi bar. So then the question is whether or not can we find an assignment to these xi's that would make the whole cost function true. So 2 SAT problems are then decision problems. In order to use quantum annealing to solve these problems, we need to reformulate these problems into Eisenhamiltonian. And for doing this, we have this mapping function, which maps each clause of our problem onto some Hamiltonian. So the set of problems that we work with, they vary in size from 6 to 20 variables, where each set of problems has either 100 or 1,000 problems. The number of clauses in each problem m is equal to n plus 1, where n is the number of variables in the set. And the interesting properties about the resulting problems is that they have a ground state degeneracy of either 1 or 4, and the first excited state is highly degenerated. One remark that I would like to make at this point is that the 2 SAT problems are decision problems, but once mapped to the Eisenhamiltonian, they become optimization problems. Okay, so this brings me to the first result for today, which is the scaling of the minimum energy gaps using the standard quantum annealing. And for this, as I mentioned before, we have these set of problems where we have either 100 or 1,000 problems. So in this case, we have 1,000 problems corresponding to each set. And what we do is to compute this minimum energy gap between the ground state and the first excited state for all the problems in all the sets. We then sort these minimum energy gaps and compute the deciles such that the first decile, D1, would constitute the smallest 10% of the gaps. So this should then include the problems that are hard for quantum annealing to solve. And similarly, D9 should include the problems with the largest 10% of the minimum energy gaps. So first observation from this plot is the fact that the minimum energy gaps close exponentially as the size of the problem increases. And the median, which is given by the fifth decile, in this case, scales with an exponent of minus 0.529. So this would mean that the annealing time that is required to ascertain an adiabatic evolution should also scale exponentially, and that with an exponent which is twice as large. So in this case, we should expect the scaling of this annealing time to be with a scaling exponent of 1.058, which is worse even compared to a simple enumeration of all the states of this problem, which scales with an exponent of 0.693. So that is what the prediction was. Now we come to the results for quantum annealing. So here we see the results for the scaling of what is known as TTS 99, which is the compute time required to obtain the solution of our optimization problems at least once with 99% certainty in multiple runs of the algorithm. So here I show the results from both simulations and from the D-wave quantum annealer. So from the simulations, and okay, first of all these results do indeed show an exponential scaling of this TTS 99. From our simulations, where we choose long enough annealing time. So the annealing time of 1,000 in our simulation corresponds to about 50 nanoseconds in the D-wave energy scale. And for this annealing time, we find that the median indeed scales with an exponent which is close to the scaling exponent predicted by the scaling of the minimum energy gaps. However, for short annealing times like TA equal to 10, we find this scaling exponent for the median to be much smaller than this theoretical prediction. And we conjecture that this comes from some non-adiabatic mechanisms, for example, fast annealing, which I'll talk about in the subsequent slides. However, from the D-wave quantum annealers, using the default annealing time of 20 microseconds, which is significantly larger compared to this annealing time that we use in the simulations, we find that the scaling exponent is actually quite small than the theoretical prediction and from the simulation in the ideal case. And such a deviation between these scaling exponents then hints towards the presence of certain imperfections in the D-wave systems, for example, temperature effects or noise, which then result in a better scaling for the set of problems that we have. Okay, so far, while we were talking about the scaling efficiency, we were talking about set of problems that had a ground state degeneracy of 1. So at S equal to 1, there is a unique ground state for these problems. But now, as we shift to study the sampling efficiency for these problems, we now concentrate on the set of problems with a ground state degeneracy of 4, which we denote as psi 01, psi 02, psi 03, and psi 04. Okay, so first I show the results for the simulations. And here I show instances of two 14 variable 2-sat problems. First, problem instance A, which was actually found to be the case for a majority of the problems in this set, where we see that if the chosen annealing time is sufficiently long, then the sampling probabilities are fair. And when I say fair, I basically mean the fact that all these 4 ground states of these problems can indeed be sampled. In such a case, when we choose the long annealing time, the total success probability is also quite large. So it's quite close to 1. However, there were a few cases where, despite of choosing a sufficiently long annealing time, 1 or more ground states were found to be totally suppressed. For example, in this instance, we find that the sampling probability of this state size 03 was close to 0 for this problem. Then we wanted to see what happens if we then submit these problems to the D-wave quantum annealer. And in this case, we could not, both these problems, so instance A and instance B, were found to be sampling the 4 ground states fairly, which is good news for D-wave at least, because then you can sample all the solutions to the problem. But to understand what really is happening, we take a closer look at this problem instance B, where we found the 3rd ground state to be suppressed. And for this problem, we know that the 4 ground states are just given by these vectors here. And now if we regard ourselves to be in the limit of S close to 1, we can regard the annealing Hamiltonian as basically the problem Hamiltonian with the initial Hamiltonian added to it as a small perturbation. So if we limit ourselves to the subspace of these 4 bases, the ground subspace, then we can write this perturbation matrix here, which for this case turns out to be this matrix. So in the long annealing time limit, it is the ground state of this matrix that determines the sampling behavior of the 4 ground states. So for this particular case, we should then expect the sampling probabilities of the 4 ground states to be 0.5, 0.25, 0, and 0.25, which matches well with the results that we have from the simulations for such annealing times. However, again, the deviation of the results from the D-wave, in this case from the simulation results, hints towards these imperfections in these devices. Okay, so far I talked about the standard quantum annealing results, and now we shift to the effects of introducing certain modifications to quantum annealing, and we do this numerically through our simulations. And the first modification is that of the addition of an additional term to the annealing Hamiltonian, and this is what we then call the trigger Hamiltonian. So we require that this trigger Hamiltonian vanishes at the beginning and the end of the annealing process, so as to preserve the initial and the final ground states. And this trigger Hamiltonian that we have here was chosen to be of this kind, so with transverse couplings of this form, with parameter G controlling the strength of this trigger. So we could choose the strength of the trigger to be either 0.5, 1.0, and 2.0. Furthermore, we could choose 2 different kinds of these trigger Hamiltonians. The ferromagnetic trigger Hamiltonian, where all these Jij's are 1, and the addition of this trigger Hamiltonian still keeps the total annealing Hamiltonian as stochastic. And then we have the antiferromagnetic trigger Hamiltonian, where these Jij's are -1, which makes the annealing Hamiltonian non-stochastic in the computational basis. Okay, so before I go to the results with the scaling of the minimum energy gaps with the addition of the triggers, I would first like to discuss the effects of introducing these trigger Hamiltonian terms to the values of the minimum energy gap itself. So for this, we concentrate on the set of problems with 18 variables. And here I show a plot of the minimum energy gaps resulting after adding the ferromagnetic trigger Hamiltonian as compared to the minimum energy gaps obtained from the standard quantum annealing Hamiltonian. So the fact that all these points lie above this solid line here means that the minimum energy gaps after adding the ferromagnetic trigger Hamiltonian were found to have increased for all the problems that we were looking at in this set. And this enlargement in the minimum energy gaps increases as the strength of the trigger was increased. However, with the addition of the antiferromagnetic trigger Hamiltonian, we found that the minimum energy gaps could either increase or decrease. And the addition of the antiferromagnetic trigger led to some significant changes in the energy spectra of these problems, the most prominent of which was an increase in the number of anti-crossings between the ground state and the first excited state. Okay, so now to the scaling of the minimum energy gaps again. So we see that despite of adding these trigger Hamiltonians, the scaling of the minimum energy gaps remains exponential. However, the resulting scaling exponents are significantly smaller, especially for the ferromagnetic case. So in this case, we find that the median, the fifth decile, scales with an exponent of minus 0.212, which should mean that the annealing time required to ascertain an adiabatic evolution should now scale with an exponent of 0.424. Also, for the case of antiferromagnetic trigger Hamiltonian, we find the median to be scaling with a smaller exponent compared to the case of the standard quantum annealing results. And in this case, we could expect this annealing time scaling to be with an exponent of 0.530. Okay, before we go and test whether it's the case, I would like to briefly talk about certain non-adiabatic mechanisms that were observed with the addition of the antiferromagnetic trigger Hamiltonian, which were found to be beneficial for the resulting success probability. So the first such mechanism was the presence of an even number of comparably small anti-crossings between the ground state and the first excited state. So here I show as an example a 12-variable problem where we see that there are actually 3 anti-crossings between the ground state and the first excited state. This first one, which is comparably large, and then the second and the third anti-crossings, which are quite small. So in this case, okay, so this is a plot for the overlap of the state of the system with the instantaneous ground state, first excited state, and second excited state. And from here, we see that at S equal to 1, we start in the ground state of the initial Hamiltonian, and some of the amplitude, okay, is then transferred to the first excited state at the first anti-crossing. And upon reaching the second anti-crossing, almost all the amplitude that is present in the ground state gets transferred to the first excited state, some of which is then lost to higher excited states. However, when we reach the third anti-crossing here, all the amplitude that is present in the first excited state comes back to the ground state, which increases the overlap of the state with the final ground state, thereby resulting in a larger success probability. Another mechanism that was found to be helpful for the success probability was fast annealing, where we see that if the chosen annealing time is so small, for example, in this case, an annealing time of 10, if this annealing time is so small that the state of the system already starts to deviate from the ground state before the anti-crossing, then upon reaching the anti-crossing, there is a finite probability for some of the amplitude to return to the ground state, thereby resulting in a larger success probability as compared to this case for a longer annealing time, where the state of the system closely followed the ground state till the point of anti-crossing, and then most of the amplitude was shifted to the first excited state after the anti-crossing. Okay, so then we come back to the results for the scaling of TTS99, first with the ferromagnetic trigger Hamiltonian. And in this case, we see that the scaling behavior that was predicted by the scaling of the minimum energy gaps is actually found to hold for long annealing times. Okay, so this scaling exponent is also quite comparable, which means that we see a scaling improvement here as compared to not only the standard quantum annealing Hamiltonian, but also as compared to brute force search. Then we see similar results for the antiferromagnetic trigger Hamiltonian, but in this case, we saw the best improvements in the scaling probability in this regime of fast annealing time, small annealing times, where the non-adiabatic mechanisms play a dominant role in the evolution of the system. Okay, so with this, I come to the second modification, and this is the introduction of higher order couplings to the initial Hamiltonian. So for this, as a standard choice for the initial Hamiltonian, we have this Hamiltonian, this transverse Hamiltonian with just one local term. And then we wanted to understand what happens if we introduce some higher order couplings, for example, 2 local or 3 local couplings with different strengths and different geometries to the initial Hamiltonian. So I would not go into all the details of these results, but I would just like to briefly comment about the role of the geometries in which these higher order couplings are added. So in this work, we studied 3 kinds of geometries: the graph geometry, where these higher order coupling terms were added according to the graph of the problem Hamiltonian, or the chain or the ring geometry, where they were independent of the graph and added in a chain geometry or a ring geometry. So if we just talk about the effects of having these higher order couplings on the minimum energy gaps as compared to the minimum energy gaps from the standard quantum annealing Hamiltonian, we see that with the addition of these higher order couplings, the gaps, the resulting minimum energy gaps, are mostly enlarged. And we found that the gaps were always enlarged whenever the higher order couplings were according to the graph of the problem. And therefore, when we add the 2 local terms and the 3 local terms according to the graph of the problem, this is the choice of the initial Hamiltonian that then results in the largest minimum energy gaps. With this, I already come to the end of the presentation. So here we compare the performance of standard quantum annealing using the ideal quantum annealing algorithm using our simulations and the D-wave quantum annealers for the set of 2 SAT problems that we had at hand. And we find here in this case that the ideal quantum annealing performs, at least its scaling performance is worse even compared to simple brute force search for the solution for these 2 SAT problems. And we found that the sampling behavior or the sampling efficiency of quantum annealing for finding all the solutions is majorly fair for the set of problems, but it is dictated by perturbation theory. On the other hand, the D-wave quantum annealers were found to perform better in both these aspects for these 2 SAT problems, but then such a deviation between the ideal results and the results from the D-wave hints towards these noise and the temperature effects or other imperfections in their devices. When we introduce certain modifications to the standard quantum annealing in our simulations, we see that with the addition of this additional term, this trigger Hamiltonian, if this was of the ferromagnetic kind, we see a systematic increase in the minimum energy gaps, which then manifests itself as an improvement in the success probabilities and scaling. And in the antiferromagnetic case, we see that the addition could either enlarge or reduce the minimum energy gaps. And the best improvements in this case resulted from short annealing times, where certain non-adiabatic mechanisms can improve the success probability. With the introduction of higher order couplings to the initial Hamiltonian, we saw similar improvements as from the addition of the ferromagnetic trigger Hamiltonian, but we also noted from the study that whenever these higher order terms are added according to the graph of the problem, the resulting performance, at least in terms of the minimum energy gaps, was the best. So with this, I would like to thank you for your attention. And if you have any questions, please go ahead.
Great, thank you very much, Vrinda. A round of applause from me on behalf of the audience. Lots of interesting things. Are there any questions? If you have a question, either raise your hand or just unmute yourself and speak up, please. Maybe I can start with a question. I just need to understand a little bit more about your 2 or 3 local initial Hamiltonians that you spoke about towards the
Yes.
end. So this is always XX or XXX. Yes, I see that.
Yes.
And you said that this worked best when your additional higher order interactions were arranged according to the graph of the problem, which I guess I understand if they're XX interactions, you just copy all the ZZ interactions. What if it's a 3 local XXX? How do you match that to the problem Hamiltonian?
So for the 2 such problems, I can just look at the connectivity graph of different vertices that represents the different variables of the problem, right? So then I could make a graph of how the different variables are connected to each other. And then according to this, I could select, for example, all the terms where 3 vertices are connected. And then I add these XXX terms according to these 3 vertices, or all possible combinations of the vertices that are connected in that particular problem graph.
But if I have a vertex with, let's say, 4 edges connected to it, how does that vertex get connected with your XXX?
So I think that would probably then result in 3 terms added. So all, or 2 possible combinations, right? So if you have some vertices x1, x2, x3, and x4 connected, then you could do something like x1, x2, x3, that is 1 pair, x2, x3, x4, or something like this.
You do it exhaustively, is that?
Yeah. Yeah.
Understood. Fine. And just again to make sure I've understood your terminology, what you call a ferromagnetic trigger, I guess I call a stochastic catalyst. Is that correct?
That
just
is correct.
Language correct. Okay,
Yeah.
fine. Fine. Good. Any other questions from any member of the audience?
I have one very simple question, and that is, what function of S? Are you doing linear anneals here? Or are you, when in the simulations, for D-wave, obviously you get what D-wave gives you, but are you simulating the same thing, or are you using other functions for your anneal?
So in my simulations, I'm using linear annealing schedules, whereas the annealing schedules on D-wave are not really linear, but from what I've seen so far, that does not seem to change much about the performance for these 2 side problems.
Okay, cool. Thank you.
And sorry, I had another question here. I remember now. With this additional, let's say, XXX initial Hamiltonian, that's also decaying linearly, I guess, during the course of the anneal in amplitude. Is that correct?
Yes.
And are you initializing in the ground state of the overall Hamiltonian at t equals 0, or just of the linear, sorry, of the local x terms?
So if I choose these higher order couplings to be of ferromagnetic kind, by which I mean that they have the same sign as the 1 local terms, then that does not really change the ground state, right?
Yes.
So, yeah, so then I only choose these ferromagnetic higher order couplings.
Okay, so you haven't looked at the antiferromagnetic or different sign couplings, is that correct?
Yeah, so then I only choose the couplings which have the same sign as the 1 local terms.
Okay. Hader has a question.
Thank you for the talk. So I just had a question regarding when you presented the results with the trigger Hamiltonian, which showed that you have some improvement because of the increase in the minimum energy gap. You may have mentioned this, but I didn't quite pick up. Does that also improve the scaling with n? So when you go to very large system sizes, do you get an improvement in the scaling? Or is it only an improvement for this particular system size that you see?
So the scaling improvement is, I mean, you do not get really a scaling advantage. So the scaling behavior still stays the same. So you still have an exponentially increasing TTS99. But okay, do I have the okay? So for example, for the standard quantum annealing, where you had the scaling exponent for the ideal quantum annealing case to be somewhere around 1.205. In this ferromagnetic trigger Hamiltonian, where you observe an improvement in the values of the minimum energy gaps and as well as the scaling, this scaling exponent for long annealing times is 0.478. So in those terms, the scaling exponent is better compared to the standard quantum annealing and the brute force search, but the scaling behavior in itself is still exponential.
I see. Okay. And I mean, just to check as well. So the difference between whether you have exponential or polynomial, is that related to sort of the order of the phase transition that you have when so the nature of the critical point?
Yes.
Okay, so that essentially doesn't change.
Yeah.
Yeah. Okay. Right. Thank you.
Any additional questions for Vrinda? If not, let's thank Vrinda once again for a very interesting presentation. Thank you very much.
Thank you.
And we'll conclude there. And I look forward to seeing you at next week's seminar. Goodbye, everyone.
Bye.
Bye-bye. Thank you.